Hello, everyone. I'm Azumi Barker, Program Manager for OpenACC and Open Hackathons. On behalf of OpenACC, I would like to welcome you to today's webinar, Accelerating a Production Solar MHD Code with Fortran Standard Parallelism, and introduce our presenter, Ronald Caplan. Ronald is a computational scientist at Predictive Science Inc, where his research focuses on the development and optimization of PSI's bottles used to study the solar corona and heliosphere. Just a few housekeeping items. All attendees will be muted during the webinar. However, you can ask questions by typing them in the chat or the Q&A area provided on your screen, and we encourage you to do so. If you would like to ask a question verbally, please raise your hand through the platform or let us know in the chat, and our event moderators will unmute participants as best we can. Ronald will answer questions throughout his presentation. We are recording this webinar, and it will be available for viewing 1 hour after the webinar concludes on the Zoom platform. You will receive an email shortly after the conclusion of the webinar and a link to the recording. Additionally, the recording will be available on the OpenACC website. So without further delay, here is Ronald Caplan.
Hello, everybody. I'm Ron Caplan from Predictive Science Incorporated. I'm going to be talking about our experience porting over, or mostly porting, our OpenACC MHD code called MAST to do concurrent using Fortran Standard Parallelism. This is a talk that was previously given in a shorter form at the 13th ASHES workshop at IPDPS a couple months ago, and there is an archive paper that I've listed here for more details that you can go to down at the bottom of the slide. So first, I'll briefly just go over accelerated computing, although anyone who's here probably already knows about that. And then I'll talk about directives versus standard parallelism. I'll discuss a couple of our previous implementations that we've done, and then I'll introduce the MAST code, and then go through a detailed journey of converting our OpenACC to do concurrent. And then I'll show some performance results, and then sort of wrap it up with a summary of kind of the current status of using that. So why use accelerated computing? Well, first reason is overall performance. GPUs versus CPUs over many decades, over decades now, has larger flops, more memory bandwidth, and recently has specialized hardware like machine learning and deep learning tensor cores. So in our case, the memory bandwidth is what speeds up our codes. And also it has compact performance. So you can create, this is a picture of our in-house workstation called Pella, which has 4 GPUs in it. And we can do pretty hefty simulations just on a single desktop on a regular 120 volt line. And it also reduces HPC real estate. I'm sure if you've seen the NVIDIA keynotes where they show one rack doing the work of 20 racks of CPUs. And it has efficient performance. So it has lower energy use, which can save money. So these are kind of the reasons for our main focus is on the memory bandwidth advantages and the in-house workstation advantages, although we do use them on supercomputers too. So let's talk about directives. So programming for GPUs can be a little bit challenging. There's many different APIs now to do GPU programming, but directives are a really nice way, and they appear as special comments in the code that direct or allow the compiler to generate code that the base language doesn't support. So this could be parallelism on GPU or CPU, GPU offload, data movement. So here I'm showing an example of OpenACC and OpenMP target offload. You can produce a single source code base for multiple targets. So because these are comments, any system that doesn't recognize them will ignore them and just compile the code as it was before. And this is why it's sort of low risk to take one of these approaches. So you GPUize your code. And it's these are open standards, so they're vendor independent in theory. NVIDIA, AMD, Intel, GCC, Cray, Flang. In practice, in terms of maturity of implementation, there are vast differences, but and they're really good for rapid development, and they're also extremely good at accelerating legacy code. So you have some old Fortran code that you want to put on the GPUs, it allows you to not rewrite the whole thing. And the 2 major directive APIs right now for GPUs is OpenACC and OpenMP. So what's Fortran Standard Parallelism do concurrent? So this was introduced back in 2008 in the ISO standard Fortran. And I have an example of it here on the right, do concurrent. And it indicates that the loop can be run out of order with out of order execution, that there's no data dependencies. It does not guarantee that it can run in parallel, according to the standard. So, however, this can be used as a hint to the compiler that it may be parallelizable. And there's currently no support for things like reductions or atomics or device selection, conditionals, all sorts of other advanced things that are in directive-based programming. But in the next Fortran standard, which will be this year, 2023, they are going to actually add reductions to do concurrent. So here's just a quick example of some compiler flags on how to activate do concurrent parallelism in NV Fortran, IFX, and G Fortran for CPUs and GPUs where applicable. You can just refer to this later. Okay, so directives versus standard parallelism. Why would you want to use this instead of directives? Right? I just got finished saying how great directives are. Why would you want to move to do concurrent? So 1 second. Okay, there we go. Oops. Sorry, slide went. Okay, so one reason is longevity. Do concurrent is part of the ISO standard of Fortran, which means if you write a code with do concurrent now, it's almost zero chance that it's going to be deprecated. You can still compile and run codes from 1972 or 1978 on Fortran today. So once it's part of the ISO language, you can pretty safe that it's not going to go away. It's also a much lower code footprint. So if you look at these examples on the right, this is the same code using the original non-parallelized code with OpenACC pragmas to put on the GPU and then do concurrent on the bottom. So not only do you not have to have all these pragmas, but you also collapse the loops down, and it's a much lower footprint. And it's also much less unfamiliar to domain scientists. So if you go to your physicist that you're writing the code with and you show them those OpenACC pragmas, it looks like a foreign language, right? Because it's talking about concepts that are not typical in regular programming. Whereas the do concurrent, it's just a do loop. And so they don't have to worry about, what default present means, for example. And one drawback, though, is that for GPUs, directives are currently more portable across different GPUs and systems, although this may change in the future. And all of these reasons for using this are also applied to codes that already use directives, because you might want to just clean up the code, and that's what we're doing here. So here's a quick little chart of the support for do concurrent on GPUs. Some of this information is gathered from this GitHub language compatibility chart by Hurton, and then through personal experience. So if you look at this, basically, OpenMP target is supported for NVIDIA, AMD, and Intel GPUs with various levels of performance, but those are all pretty well supported. For OpenACC, it's very supported and mature on NVIDIA systems. AMD, there is a GNU implementation to be able to compile for it, but the performance is a bit lacking. And on Intel, there is no support. However, Intel is coming out with a translator to turn it into OpenMP target automatically. So in a way, you could use it that way. For Fortran do concurrent, NVIDIA has full support of it on its GPUs. AMD currently has no support anywhere, but Intel officially supports it on their GPUs, although I haven't actually seen any performance results of anyone using it yet. So that's why it's not a big green button there. So by moving from OpenACC to do concurrent for NVIDIA, we're fine, and that's typically what we use. We are possibly losing AMD support, but we possibly are gaining Intel support. So either way. Okay, so in the past, we've already tested doing this with some smaller codes, a tool called Diffuse, and our potential field solver. So for our code Diffuse, this was the subject of a paper we wrote of can Fortrans do concurrent replace directives for accelerated computing, and this was for the WACCPD workshop at SC21. And what we found there was that switching from OpenACC to do concurrent didn't affect the performance at all on the GPUs, and it still allowed CPU multi-core parallelism. Then we moved on to doing this for our MPI-based code POT3D, which is a potential field solver code, and that's an open source code on GitHub. And here's a blog discussing what we did there. And there, what we found was that on the CPU, everything was the same because it wasn't using multi-threaded parallelism anyway. It was just using MPI. And on the GPU, we were able to get the same performance if we managed the GPU memory directly using OpenACC. But if we just did do concurrent only, then there was a slight performance hit using the unified managed memory, which we'll talk about later. So what we're going to talk about here is we want to apply this now to our large-scale full production code mass. So the mass code, which is the Magnetohydrodynamic Algorithm outside a sphere, it's a general purpose simulations of the solar corona and heliosphere, and it's used for solar physics and space weather research. It's on a spherical grid, and it uses a variety of numerical methods, implicit, explicit, time-stepping schemes, finite difference stencils, preconditioned conjugate gradient solvers. But overall, it's very highly memory bandwidth bound. It's about 70,000 lines of Fortran, and it's parallelized with MPI plus OpenACC, and now standard parallelism as well. And down here in the corner, there's a website where you can look at more details of the code. So let's quickly review the OpenACC implementation of mass. This is just a quick, review, I guess, of OpenACC. So this is what an OpenACC basic loop looks like. You have a parallel, and then you have a loop collapse there. Default present just means all the data is already on the device, and I'm ensuring that. You have a kernels structure, which allows you to do array syntax. You also have reductions in OpenACC, like scalar reductions on the top there, and then the bottom is an array reduction implemented with an atomic update. And to manage data, we use the enter and exit data clauses that will put the data onto the GPU device. Whenever the CPU needs it, you can update it. And otherwise, everything stays on the GPU, and then you can free up GPU memory afterwards.
Ron?
Yes.
Ron, we have a question. So
sure.
One of the attendees is asking, in conclusion, is DC more efficient and safer than OpenACC?
So that'll be the last slide. you have to wait. I'm not going to give away the ending. That'll be my answer.
We have a second question in terms of accuracy. How do the final answers compare on GPU and CPU, or are you saving that for later?
That's this. Okay, so that is a whole topic that used to be a topic of discussion in the past, and basically it's all IEEE standard. You're going to get slightly different runoff errors and stuff like that because of the way things are computed, especially with things like reductions are going to be computed in different orders. So you're never going to get bit by bit exact depending on your algorithm, but in terms of just standard IEEE double precision floating point, it's just as accurate as on the CPU. Okay, so the mass code uses multiple GPUs across a whole supercomputer. So to do that, what we do is we create a MPI shared communicator, and this is a list of ranks that are just on the single node that you're on. And then what we could do is use OpenACC to set the device number of the GPU we want based upon the rank on the node. So if we launch with 4 MPI ranks per node, and there's 4 GPUs per node, this is how you can tell the code use GPU number 2 because I'm ranked number 2 on node 10 or whatever. And then for MPI calls, we use CUDA-aware MPI, where you can use OpenACC to tell the code, use the device pointer, or use the device version of this array, and then you just call the MPI call like you did before, and it's supposed to, under the hood, just do everything perfectly. So bypass the CPU and directly communicate from that MPI call to whatever other GPUs are making an MPI call. Okay,
so we have a question.
Yes.
I'm sorry. Why are HPC applications memory bandwidth bound?
So not all HPC applications are memory bandwidth bound, but ours is, and most computational fluid dynamics codes are. And that has to do with the fact that a lot of them are dealing with stencils or sparse matrix multiplies. And so the amount of arithmetic intensity, and I'll actually show an example of this a little bit later, but the arithmetic intensity is quite low because you're reading things from memory and doing like 1 or 2 operations on it and then putting it back. And you're doing that over and over again for large amounts of data. So you just end up bypassing the cache, and you end up basically being bound by the DRAM memory bandwidth. And I'll show a good example of that coming up, actually. So our OpenACC implementation, it's a single portable source code, could use on GPUs or CPUs. Here's a quick little performance example. I won't go into too details, but basically, you know, one node of an A100, 4 A100 GPUs was almost over four times faster than 4 dual socket EPYC CPU nodes for this example. And that basically, if you calculate the memory bandwidth of each of these systems, it almost goes exactly like that. So I think this one's, I put the memory bandwidths here in the chart, and if you do the divisions versus these times, you'll see that they almost line up exactly. So there we go. Okay, so the total lines of code and the total number of lines of code is 73,000, and about 2% of them are OpenACC, and this is how they're distributed in terms of which type of OpenACC pragmas there are. So a full 1,000 of them are just standard parallel loops, and then there's a bunch of other ones shown here. And in total, there's about 1,500 OpenACC directives in the code. So before we move on to the do concurrent implementation, this is just sort of a performance check, and this will go back to why it's memory bound. So you can do what's called a roofline analysis. Insight Systems produces this plot automatically. It's quite nice. And these are for the mass, one of the most expensive kernels in mass, which is a velocity parabolic operator. And on the left is kind of an example of why. So you see here's a stencil operation. And if you compute out all the memory it has to grab, and a lot of it is not stride 1, because you have like a k+1, k-1, and you calculate the number of floating point operations versus the data, you see an arithmetic intensity of flop per byte of like 0.11. So if you look on this chart, given a memory bandwidth, here it's 900 gigabytes per second on a V100, you see that the peak flop is over here on the right, where those two dots, that's single precision, double precision. We're nowhere near there to peak flops. And so what you want to do on a roofline analysis is you want to be as close to that red line as possible. So our kernels are right on the red line. So given their algorithms, that's kind of the best you can do. The only way to optimize this would be to change the algorithms around or do fancy things to try to increase the arithmetic intensity while still keeping the total work the same. And some people have found tricky ways to do that, but this should answer the memory bandwidth question. Okay, so we want to now see, can we use Fortran Standard Parallelism instead of OpenACC? So to do this, we're going to end up having multiple versions as we go along this journey. And there's certain reasons why. So you might think, well, just do it or not do it, right? But that's not quite how things work. So we're going to end up with 6 codes. And the reason why is, do we want to avoid a bunch of code refactoring or not? Do we want to keep the code as close as it is now, or do we want to allow ourselves to refactor? Do we want to adhere to the current 2018 Fortran standard or not? Or do we want to use the new 2023? There are certain, we'll ignore this comment for now. Should we use preview and special features of specific compilers like NVIDIA or not? So for example, NVIDIA already implements the do concurrent reduction clause. It also supports OpenACC directives within a do concurrent loop, which is also not standard. Do we want to take advantage of those or not, or stay compliant with the base language? And also there's a trade-off of how many directives we get rid of versus the performance. And that boils down to using unified managed memory versus manual memory management. You cannot do manual memory management with do concurrent. You have to use something, either OpenACC or OpenMP target offload. So that might change performance. So that's how we end up with 6 codes. And we're going to sort of go through each one of these and see what's going on. So the first thing we want to do is we want to just be compliant with the Fortran 2018 language. So we're not using unified management memory. And we're not going to refactor the code. So one example of an issue here is there's no reductions. So for example, this array reduction here would need refactoring in order to avoid using OpenACC here. And so we leave it alone and we leave it as OpenACC. Functions and subroutines inside of loops in the language spec, they need to be pure functions in order to be inside of a do concurrent loop. We do have pure functions. but the NVIDIA compiler doesn't seem to support that. So we still need this OpenACC routine directive declaration. Also, occasionally we are using OpenACC kernels command around Fortran intrinsics, like this min value you see here. In order to get rid of that, we would have to expand that into an explicit loop and code that ourselves. So we're not doing that at this stage. Now, previously for our POT3D code, we found that if you use unified managed memory, it can give a performance hit versus managing the memory yourself. So for this version that we're doing now, this code 2 that we're going to call it, we're going to leave in all of the OpenACC data management directives. A little side note is that in OpenACC, you can do a parallel region and have multiple loops in there, and that will fuse those all into one GPU kernel. And you can also do asynchronous operations. For do concurrent, you don't have either of those. So that might give a performance hit. So at the end of the day, for this code, which we call code 2, we've been able to reduce the number of OpenACC from about 1,500 down to about 500. So almost 3 times lower number of directives. And this is compliant across the board. So now let's move on to what we call code 3. And this one is basically the same code, but now we're going to allow ourselves to use unified managed memory. Here's a description of what that really means. So normally you have your CPU memory, you have your GPU memory, you got to transfer your arrays from the CPU to GPU, compute on them, bring them back. With unified managed memory, you don't see any of that. You don't deal with that. It happens on its own in the runtime under the hood. So it's doing its own caching, it's doing its own transfers, and it works fairly well. So even when using this, we can't get rid of all of our data directives. There's some certain nuanced things. I won't get into too much detail. We have to leave in this declare statement because it's in a module, that's in a function call. Also, derived types, the actual structure of the derived type, this A here, A contains 3 arrays. We don't need data movement for the arrays, but we do for the structure itself. And that has to do with unified memory not working with static arrays, but only with allocatable arrays. But at the end of the day, what this has done is it has allowed us to reduce the number of ACC directives down to only 162. Okay. Any questions so far right now? We're good? Okay. So now let's move on to the next version. Now what we're going to allow ourselves to do is use the Fortran 2023 preview implementation that's in NV Fortran. Specifically, this reduce statement on a do concurrent. And so that'll allow us to get rid of all the OpenACC reductions. However, there are no array reduction support for do concurrent, but because of NVIDIA's compiler, you can use OpenACC directives inside of a do concurrent loop. So we can just put this atomic updated there and convert the loop to do concurrent. And this allows us to remove most of the data clauses and including the derived type stuff. There are a few directives remaining. I list them here. We won't get into the details. But then this one now, we've only have 55 directives in the entire code of 70,000 lines. Okay. So, but we want 0, right? The idea is like, how far can we push this and really just have pure Fortran with no OpenACC? And that's where we have code 5. And here we have to allow ourselves to refactor the code a little bit. So first thing we do is we take out the kernels and we expand min-val into our own implementation of it. The array reductions, if we flip the loops and change it around, you can actually not use an atomic and just a simple reduction. And so, which I show here. And so we got rid of those OpenACCs. And then the last thing is the set device number. So to choose the GPU you're going to compute on. Well, that was a tricky one to get around. And thanks to Jeff Larkin, we were able to do it. So basically, if you create this little bash script here, this is using OpenMPI. You can use this bash script to say, only set the CUDA visible devices to my local rank of the shared communicator. And this is in the environment level, and then execute the program. And so instead of launching the code, you launch this script, which launches the code. And by doing this, you can have the same type of device selection automatically, because the OpenACC will just run on the first GPU it finds, and there's only one visible for each rank. So this actually works, and that gets us that last little directive out. The other thing that we had was these directives for function calls and for functions that were called inside of a parallel loop. So to do that, we just inline those functions, and the NV Fortran compiler has an inline feature. It would not automatically inline certain functions, so we had to explicitly declare them. And I'm going to skip this last little comment because that's a detail that's not needed to be talked about here. So with that, we have no more OpenACC in the code at this point. If you see the compile line here on the bottom right, you can see where the inlining function call is there. But basically, we're just using standard par equals GPU. There's no more OpenACC at all. The number of lines of code have gone down to 69,000 lines. And this is just now a pure Fortran code. Okay, but we have one more code, because spoiler alert, the unified managed memory has a big performance hit when you're doing MPI across GPUs. And we'll see that in a little bit. But because of that, what we want to do is say, okay, what's the minimum number of OpenACC we can use and still get the same or roughly the same performance as our original code? And so for that, what we do is we take the code that has no OpenACC in it, and we just put back the data directives. And that's what we call code 6 down here. And doing that, we only need 277 directives total to do that.
So
okay.
Ron, there
Yes.
was a question in terms of the refactored lines. The question is, how many refactored lines of code, though?
So thankfully, in our past implementation of OpenACC, when I did that, I tried to not use kernels as much as possible, because the GNU implementation of OpenACC had a big performance problem with kernels. So luckily, there were only like 2 or 3 places in the code where we had to refactor and write explicit loops out. In another code that used heavily used kernels, for example, that might be a big step to do. And certain Fortran intrinsics right now actually do get parallelized on the GPU when you activate do concurrent on NVIDIA's compiler. For example, matmul will actually go on the GPU. However, things like minval or minlock do not. So currently, you do have to expand things like that. And if you have anything in array form, there is a way to do a do concurrent on array form, but in my opinion, the way, if you look at how that looks, you might as well just write the loop. So if you have a bunch of array syntax, that would be a big change. In our case, I had already changed a lot of those over when I did the OpenACC for performance reasons, because using the OpenACC loop collapse ended up being the best performant version. So versus kernels. So yeah, that's a good question though. Okay, so let's now see, how do all these codes perform? So we're going to use a medium-sized production thermodynamic kernel relaxation test. I have a little picture of it on the right. Has 36 million cells, and it runs for 24 physical units of time. And this is chosen so it can fit onto a single 40 gigabyte A100 GPU. So the first test we do, this is using the expand system at SDSC. What effect does this have on the CPU only runs? Like, did we mess up the CPU performance? And the performance is identical. And this is mainly due to the fact that we don't do any hybrid CPU parallelism. So it's MPI only. So each rank is just one thread. And therefore, whether it's do or do concurrent, the compiler doesn't care. It's not doing anything different. And so you see the performance is identical on the CPU. So that's great. For our GPU test, we're going to use the Delta system at NCSA, and we're going to use a single node that has 8 A100 GPUs on it.
So there's a question of,
yes.
Have you tried unmanaged memory versus unified memory for computation and compared the results?
Yes, and we will see that very presently. So if out of those 6 codes that we went through, 3 of them are using managed memory and 3 of them are using unified memory, and we are about to see what effects that has. And well, here's a list of the codes, right? So all the codes, if you see their little tags, the 1, 2, 3, 4, 5, 6, anything with a U at the end is using unified memory. So the codes 3, 4, and 5 are using unified memory. 1, 2, and 6 are using managed memory. But you have to use unified memory if you don't want to use any directives at all. So that would be code 5 here. So here's the performance. This is the figure for the whole talk in a way. So let's focus on the black, blue, and light blue lines. These are the codes that are using managed memory. And the black circles are the original OpenACC code that we've been using this whole time. And if you look at the codes 2 and 6, they have very similar performance, not exactly the same, but good enough. And but if you notice, code 6 only has 277 OpenACC directives versus 1,500 for the original code. So that's a huge reduction. So another thing to point out is remember that code 5 has absolutely no directives at all. However, if you look at the performance of code 5, it doesn't look that great. So code 6 has 5 times fewer directives than the original code. And code 2, which is the spec compliant version, that has about 3 times fewer directives with similar performance. So that's great. So we can reduce the directives a lot and still get our performance. But now let's talk about those orange lines. So codes 3, 4, and 5 show poor performance and poor scaling, and all of these are using unified managed memory. So that's pretty much a smoking gun as to what's going on there. In fact, if we take code 2 and we just run it with unified memory, even though the data directives are there, their data directives are ignored, and we get exactly the performance of code 3. So let's look a little deeper here. So on one GPU, I have the results over here on the right, between the MPI time and the non-MPI time, and you see that all the 3 unified memory codes in the middle have this performance hit. But it seems like it's sort of both in the MPI and non-MPI, although that might be a little misleading because the MPI includes load and balance, and so some of that is due to transfers going on as well. Okay, so what about on 8 GPUs? So if you look on 8 GPUs, the situation is even worse. So now if you look at the unified memory, the MPI is taking almost half the time. And there's also, if you look at those error bars, there's huge variability on how fast it goes. And so the unified memory with the CUDA-aware MPI is just not doing it. And apparently what's happening under the hood is that it's actually not using CUDA-aware MPI. It's actually doing transfers to and from the GPU every single time. And the NVIDIA compiler developers are aware of this issue, and they are currently working on a fix for this. So hopefully, yes.
There is a question. Is there a reason why the codes with unified memory are plateauing with increasing number of GPUs?
I think it's because the MPI time is rising, and so it's sort of saturating. The reduction in the computation time is no longer meaningful because so much of it is MPI time now. So, and so that's what we have over here on the right on the bottom. You can see that there. So now this is across architectures. So here I was nicely given access to an H100 by Georgia Tech on the Quorum machine. And if you look at one GPU results, all the codes run faster on the H100 versus the A100 as expected and commensurate with the memory bandwidth, which is great. But once again, you see the unified memory codes are slower across the board. So this isn't like a GPU specific issue, it's a software issue. So
another question.
Yes.
Do you pass the GPU data pointer to the MPI in the cases in the middle?
So because we don't have data directives, we don't have an OpenACC host data directive. So there's nothing telling the compiler specifically use the GPU pointer because the code itself is just straight Fortran, right? So the runtime or the compiler has to determine what to do there. And that's where this issue is cropping up. So basically the compiler doesn't quite get that it should be passing the GPU pointer there, and is actually passing the CPU pointer. So the MPI runtime has to trigger a transfer from the GPU to the CPU and then back again. And it might even be doing that twice, depending on the implementation. So this is an issue where there is no way within Fortran. Fortran doesn't know about different memory spaces. So it has to be the compiler itself has to, put in the code as if there was an OpenACC host data there. And that's not the most simple thing to do. There is some triggers you can do to make the compiler think that it's always on the GPU, but that might not always be the case either. So they're basically working on a fix for this down the line that should hopefully make this a non-issue eventually. But in the meantime, you could just use managed memory and it should work. So like I just said, the managed memory is not utilizing the CUDA-aware MPI here. So there's a lot of GPU, CPU transfers. And we can see this using the Insight Systems profiler. So using this command line here. So if you look at code 2, which is using managed memory, what I have outlined in this white rectangle here is one solver iterations. And you see these blue bars are computational kernels. And the little scattered bits over there to the left of the blue bars is the GPU peer-to-peer data transfers. So it's sending data through the MPI directly from one GPU to the other on the node. However, when you run code 3, which is using unified memory, but otherwise the code is the same, one solver iteration is this entire block, and you see how much longer it is. But if you look at the blue computational kernels, they're actually the same size as the ones above, right? But there's bigger gaps in between them. And if you look at this first big gap with all this pink and green, those are GPU, CPU data transfers. And this is where and this was on 8 GPUs. So this is where this overhead is happening. And there's also additional overhead in between the computational kernels as well for things like sending in scalars and back and forth into the kernels and array descriptors. So this is basically pinpointing the issue. And so this is being worked on. So what did we do? So we've shown all this, and for our production code, we actually do want to go to standard parallelism. It's a sort of a route that we like. And so what we ended up doing is creating 2 versions of our code. The main code has the absolute minimum OpenACC directives that we need so that it can be compiled on GPUs using unified memory. So in our code, this ends up being 132 directives, which is only 0.2% of the total lines of code. We also create a branch, which is a direct duplicate copy of the main code, just with OpenACC data movement put back in. And that raises the number of directives to 593, which is 0.8%, but that's still a lot lower than 1,500, which we had originally. Also, most of that code is reductions and other things that might be eventually able to go on do concurrent as well. So the branch version here is what we use in production. So since the developers aren't looking at it, we can just compile it and use that when we do production runs. The main branch is easy to develop because there's basically almost no OpenACC in it at all. And so just 100 lines. So we've also added OpenMP to the OpenACC loops. And the reason we did that was our code was never been CPU hybrid before, but now it can be because do concurrent can be multi-threaded on the CPU. So by adding the OpenMP to the few loops that aren't do concurrent compatible, we're able to add the hybrid CPU parallelism to the code, which we never had before. And we may actually convert that OpenMP to target offload for use with Intel GPUs, because the Intel compiler also supports do concurrent offload to their GPUs. And so if we add OpenMP target for the reductions in other places where we couldn't use do concurrent, then it might open the door for us to use Intel GPUs eventually. So let's summarize this. So do concurrent in Fortran for accelerated computing. This is kind of an overview based on our experiences. Good things. 1, it's ISO standard. There's basically 0 chance of it being deprecated. It's much more compact and simple code. The loops exhibit similar performance to directives when combined with manual data movement. And it can add hybrid MPI threading CPU parallelism to codes that don't already have it. And it's currently supported by NVIDIA and Intel for their GPUs. Drawbacks is there's some lack of performance features. There's no asynchronous computation. There's no kernel fusion. There's no memory management. There's a non-trivial performance drop for CUDA-aware MPI with NVIDIA if you use unified managed memory, but there is a fix in progress. And there's no current support for it in GCC or the AOCC or AMD compilers. Cray, I think, is wrong. I think they actually are adding support, Cray. So this means basically there's no AMD support at all right now, although some of these are in progress. So the basic conclusion is we still need OpenACC or OpenMP target for some time. That's not going away anytime soon. But future language additions and compiler support for multi-vendor accelerators could lead to one code to run on them all, right? And that's the end goal for everybody, basically. And so currently, right now, we've been able to make the code much more readable for domain scientists using do concurrent, because most of the loops are just regular do concurrent loops. And we sprinkle in the OpenACC that's needed. And as things progress, then we'll have less and less OpenACC. And so that's basically, I think that's it. And once again, you can go to this archive to look at the paper for more details.